Thank you. Thank you. Honored to be here in the biggest room here in this event. So also I keep you here from the panel and podium, and I hope I really make it exciting. So I have to get you a little bit warmed up for the panel so that everybody is active again. The topic I talk about is quantum computing and demystifying it. Who has used a quantum computer before? Okay, not that many today. Right, no, I can understand it, and I will shed some light on it. Of course, we don't go into too much technical details, but we are here around also tomorrow, so if you have more interesting questions, feel free to approach us. I was already kindly introduced, so I just directly start with perhaps some of the interesting aspects when we come to real application problems, because the talk should be also in the light what we can do today. Right? Because quantum computing has been there for a decade, everybody talking about it. What is now really some things we can really use it for? And one of the application areas you see here, where actually the University of Iceland is very strong in, is remote sensing, Earth observation. You see that with satellite data, which is giving you the land cover, but also basically multispectral and hyperspectral data within the Earth. So quite complex data sets, which are quite nice. And what we do with them, we use machine learning. So there are different ideas of using support vector machines, more traditional classifiers, more traditional machine learning, or as my previous speaker also said, deep learning. Right? So new technologies in image recognition. And we motivate this example a little bit, and throughout the talk we will come back to it and see what quantum computing has to offer to solve these problems today. What we use basically on a daily basis, we train machine learning algorithms to determine if this pixel in this, let's say, image is a forest, is a river, is a tree, basically pixel-wise, not scene-wise, as you rather have in the automatic car that we just have seen. So, and we use here a traditional classifier, support vector machines, very robust material, not so hard to train like deep learning, and that's why it's a good motivator to see what quantum computing has to offer. So this is more on the practical side, and what we do with it, we use, of course, high-performance computing today based on 0 and 1s, things you know, right? A classical computing style. That means large systems, parallel computing, and we break down, for instance, the training of a support vector machine here down from, let's say, 15 minutes to 1 minute for one parameter set. Doesn't sound so much because, of course, we don't know the best parameter. This is one of the unsolved challenges in machine learning. What is the best parameter set for the machine learning algorithms? So we have to search the whole space, and for this we do that in parallel, using parallel computing, and then we are able to break down the time from 9 hours to half an hour. And then it becomes much more interesting to use parallel computing. Of course, we do this not only with traditional classifiers, we also use deep learning. Here's a ResNet 50, kind of the cutting edge in image recognition, if you want, but it requires huge amount of training time. But luckily to the rescue, also their high-performance computing has frameworks of using different so-called graphical processing units together with Horowot, with TensorFlow, and then you see on the slides, we can nicely also break down the training of these to a couple of minutes using these technologies. So essentially, in a nutshell, what you have is computing was essentially always something where we had zeros and ones and many long ways of it. I think many of you know that from Computer Science 101, or when you started basically doing anything with computing. Now, interestingly enough, we had also these paradigms of CPU, and then the era of many-core and multi-core came. So multi-core CPUs is something we use today. It's a very high single-thread performance, so cutting edge in CPUs. Unfortunately, they get very hot. So we cannot really improve much on that to make it better, to make it faster. So what the communities came up for rather instead is something we call the many-core, which means more moderate processors, basically, but then hundreds and thousands of it to enable scalability for rather smaller jobs. But then with this, being able to really train deep learning networks that we have seen at scale. And this is very nice technology, but they all share in common that we have the same classical computing style with 0, 0, 1, 1, 1, 0, 0 that you know. So we use it in all the application fields today, starting from science and engineering that you see in all the different disciplines. up to business, of course, when you go to the different applications we have seen all over the day, starting with Mara in the morning with deep learning, of course, up to just as previous speaker with autonomous driving. So what's new? So what is now the difference when we start thinking about quantum computing? What is the idea behind it? And this is traditionally something which is a bit more complex to teach. That's why here and there you see some animations. But the essential characterization is that we have quantum physics. And this is an interesting effect when you cool it down to absolute zero, where we find something like qubits existing. And qubits, as you see here, can exist as 0 as 1. And with a kind of current that you can enable, the circulating current that you see there, enables a magnetic field which is either up and down, which means essentially, again, the 0 and 1. But giving the quantum effect that we have, according to physics, and that we will later see is also implemented, it is 0 and 1 at the same time. We call that superposition. And this is one of the properties which enables a quantum computer to enable very interesting things. And with this, we have also lots of different possibilities. Basically, if you think about 1,000 qubits, that's what existing today, also 2,000 is coming along. And then basically you have something like 2 to the 1,000 or 2 to the 2,000 possibilities to program this particular quantum computer. And when you think now, okay, that was 1 qubit, boring. We want to have 1,000 or something. How does it look like? And how is it really, you know, basically on the chip? How it is available on the market right now. So you see there is a quantum chip. It is maybe not so different than other chips you know. But the interesting property is that there are different qubits. They are together, and they influence each other. And we call that a coupler when we bring them together. And when we bring them together, we can basically say that the coupler can either favorite the same state. You see that here, 0 and 0, or 1 and 1. So that's how you get 2 qubits interacting with each other. And this will be another interesting property when we think about the quantum device at large in the end. And here's the example where you have them basically on the opposite, the neighboring qubit. And when you want, this is a way how you have then a quantum device. You start with having qubits, many of them. You have many couplers, coupling them. And then there will be something which is more about managing magnetic fields. I come to this later. But these are the key ingredients, essentially, you see there on the chip. Now, when we come more to the property that is then the quantum physics phenomena, really, you see that essentially by influencing each other with the kind of coupler that I just pointed out, you have something that you have to see these qubits as one complete entity. So it's basically from the physics perspective, one quantum object, and they are basically then handled and treated together. That means suddenly that our state that we have actually grows, right, from 2 that we have seen now to 4. And they are basically sharing something which we call then the entanglement. So they are basically have to be considered together as one physical object. And now this is now bringing us from 1 qubit to the chip with many qubits, circulating loops, and then the currents with magnetic fields. Now the question is how that is enabled by the physics, and there's a challenge with this. That's why not everybody raised your hand here of not having used a quantum computer yet. And this is of course a cooling. So unfortunately the qubits only behave quantum mechanically if they're cooled down. And this means absolutely 0, meaning that you have a large device around it, essentially bringing it down, you see here, from 50 Kelvin down to absolute 0. And the processor that you see basically is just a tiny part at the end, basically, of this particular device. There's another problem, vibration. Everything which is around previous or external magnetic fields, radio frequencies, all of this is a hindrance to this quantum effects. So another one that you need is a big block, a kind of shield, to basically have an environment which is very, let's say, positive for the quantum effects to work. And you here see one example I don't talk much about the name of the company because we shouldn't do so much marketing, and they can be sure I'm not paid by them, so I'm a scientist and a researcher. But of course, we use concrete techniques in order to bring the quantum computing forward. And the system that you see there is again the quantum processor, and the way it's basically shielded by the outside environment with the cooling. You could say maybe a bit salop, as we say. Essentially, it is standing in the fridge, the quantum computer. And that's actually true. The interesting thing with this particular device is you can buy it on the market. Hence, you see here some of my bosses in Juelich at the Supercomputing Center. We bought such a system in Juelich. And there's Christel Michelsen, which is important to mention because she is driving the quantum activities quite much in Juelich and actually in Europe in general. And then Thomas Lippert just beside her, who is also a very high capacity in HPC and also driving these efforts together. So essentially what we have now is something like an infrastructure in Juelich for quantum computing. We call that UNIQ, and it's in many ways unique. And I don't show that here to say JUNIQ has such a computer. I much more would like to show you the perspective how you would use such a device. Right? When we now think about that we have already HPC computing, we know that for numerical simulations, we know that for doing Spark with data analysis and so forth. So how it looks like and how we operate this. We in the DEEP project, it's a European project, we developed something called the modular supercomputing. And this means that today our users don't have homogeneous workloads, right? They have numerical simulations, they have data analytics, they have scalable workloads, high throughput computing. So essentially we have a supercomputer which is quite diverse. And essentially like you use the accelerators with GPUs today, right? You see you cannot do general purpose computing usually with them. They're based for deep learning training, matrix vector multiplications. That's what they're very good in. For other stuff, you use still the multi-core CPU. Hence, they're more accelerators, right, for certain problems. And in a way, you could see that the quantum device and also the neuromorphic devices, which are actually also knocking on the door already, will be just a module that you almost like an accelerator, just use for specific problems. And then you come back to traditional computing. So for at least the next years, we definitively don't see that quantum computing will now change everything we do. Instead, it will be a helper in several specific problems, and this is what I will point out. Of course, not to mention that in research, we're not happy just with one computing company that is offer that on the market. You see here on the side, there's lots of activities simulating qubits up to other annealers, other computing power in terms of quantum computers which are coming to surface, and there will be probably much more given the quantum flagship and so on, which is actually in Europe. But that's how you actually use that. Now, to be frank, we also have to check a little bit related work, because what I talked about a little bit and will talk about is a specific form of quantum computing called quantum annealing. That's important because it has a little bit more easier access to this problem in terms of quantum physics. And by this I mean the control. Usually you set up a problem in the quantum space, we come to this with an SVM, and then the evolution is going after quantum physics and will then evolve to 0 and 1s at the end. Then we are happy. There are other forms of quantum computing called, for instance, the gate model approach, which is much more hard. You try to really control every little qubit, the evolution in the process, and this is very, very hard, so you have just 10 qubits or maybe less than 100 these days, which you can really work with. And this is, of course, for really practical application problems. That's what the talk is about a bit. So this is not useful yet. So, and additionally, you don't really can buy them on the market very quickly. So hence, you have to think about that quantum computing is a very large field, evolving, and I can encourage you to study it. It's quite interesting. You see there on the bottom, there are lots of different approaches. The one I'm telling about with the annealing process is really something which is more to the adiabatic side, but there are different other approaches around. Now, why I'm telling all of this? When I think I'm a practical guy doing machine learning publications all day, using high-performance computers, where it's useful. Why I look into quantum computing. So the relevance is clearly expressed in optimization although there's also another one called sampling. I cannot talk because of time constraints here. So in optimization, what we want to achieve is to find a hopefully global minima of a kind of energy space, a surface that you see essentially here. And no matter you have all traditional support vector machines and quadratic programming, or you have the kind of ResNet 50 deep learning cutting edge, it's always behind it is solving an optimization problem. And with this is quite complex. So it's not that easy to do this, to find the minimum of a function, and hopefully then the global one even, because there are lots of traps getting actually somehow caught up in the local minima. So, and finding the lowest global minima is something which is shared in engineering and in sciences and in the business world across all different applications. So you can see that quantum computing, when it gets more and more qubits, then we really have lots of applications which we can actually apply our elements through. So the interesting thing is now to compare it maybe, right? So we have done this, of course, in the past. We train neural networks now. What is now the interesting effect that's taking place? And this is something we call the water tunneling, or effectively quantum tunneling, but there's a water analogy to it. And the water analogy means essentially that we have the landscape that you maybe know, the energy that I just had, usually checked just in our local surroundings, right? With some elements that you know, stochastic gradient descent, some optimization algorithms in the past. Quantum computing instead puts water over the energy space. And with this, by changing then the magnetic fields, and automatically the water will find the global or nearly optimal solution. And this makes it very attractive for many of the application problems to have a check if that's really true, to find these global minima. Because essentially what you have is that this, when you train a machine learning algorithm, when you have deep learning, this is a computing intensive part, right? This is iterative. I search for the minimum, I have something like there. I want to go to the valley, but the valley is maybe behind the next peak to go to a lower valley. So I have to do something which is, you know, then very much cumbersome, finding the right optimization algorithm, having the certain learning rate, momentum, lots of tuning. But in the end, what we want to achieve is to hopefully land at the global minimum, which is not easy to find for traditional computing. But for quantum computing, it works through this quantum tunneling effect, when the qubits are entangled and cold to zero, go down to absolute zero. So this is, of course, now a motivation to think about it, what we can do it in terms of applications, and what I also want to convey at the end here in this process. Of course, at the end, we talk about something called collapsing, because by now you want to think, okay, when we have this tunneling, what I can read out as a user. Do I have a Python API, get our results back? Of course, right? At the end of the annealing process, where we come to now in a minute a bit, we have the superposition, but it is actually collapsing in 0 and 1 again in the annealing, right? So we have concrete values we get out of it. Now is the question rather how to program it. I see already some faces here, Java developers and Python developers, that think, is there an API, or how do I influence this thing, right? We are computer scientists, or many of us, engineers, that want to influence this. We don't just want to watch and say the quantum computer is doing the thing. And normally we have to do something. So what are the two, let's say, general paradigma what you can do with such a quantum device? And this is firstly the element that you see on the first video, where we have this kind of energy field again with the superposition, magnetic field. And what automatically is inside that is, of course, we call a double well potential. So you could say in the end it collapses to 0 or 1. So there's a potential in the magnetic field. So essentially, we have this interesting valley, and it's 50% chance. It could be 0 or 1. 50% chance is not nice when we know something about a problem, and we know how support vector machines work and elements. So we can influence this process. Influencing this process means we play around with the magnetic field. So we have a handle on this. We can actually steer the probability of either falling to 1 or 0 with this bit. And in this case, we have the first, let's say, programming element, how you actually program a supercomputer. Admittedly, just a qubit. But remember what we also talked in the beginning about, we're coupling them, right? And the coupling, we decide, is it basically now the same, or is it the opposite state in the neighbor? And now if you think about, of course, normally we would have a much bigger system, right? I'm just talking about the major principles of having one qubit, of having you know, a coupler with another qubit. Now real systems, of course, now connect the 1,000 or 2,000 qubits together. So this is an energy landscape which is quite huge. And this is essentially how you summarize it programming a computer, and you see also there on the video the kind of water in the end that flows to the global minimum in 20 milliseconds. Another interesting property, right? So this is something where HPC is, you know, doing iteration over EGD, SGD optimization steps, whatever, and RMS prop is a bit faster these days, but still, this is a long, cumbersome process, and here in optimization with the quantum annealer, of course, limited just to this particular purpose. To show you also that we use this in real practice, I brought you here some Jupyter notebook element which we will actually make public when this published paper that you see the reference on below is actually accepted. So then it's basically open, and as you see also access to this certain computer I will not name is possible, so everybody can actually try it out. You can get the Jupyter notebook from us to try with the quantum SVF some things. Now let's come a little bit also to the limits, right, when we approach the end of thinking about this. Where is the problem now? Why not everybody is using it? You see here some example data we really use from the remote sensing community. And what you see there is we have a 2-class problem. In the beginning, I started with a 58-class problem, right? Tree, forest, river. Here we have just 2 classes, so it's admittedly a very simple problem to do. Still, we're using an SVM for it, and the second one would be the number of data, which is definitively a limiting factor today. However, the benefit is, it is actually something you can program right now, so it's not something big in the future to come with quantum computing. You can do it right now. We use a SDK for it, Ocean in Python, very nice. And with a previous quantum computing SVM that was already created by my colleagues, Crystal and her team, actually, it's quite straightforward to program this in the old manner as you were used to have SVMs. So hence the techniques and algorithms come to place in order to make that work. And with having lots of many opportunities and possibilities here, we have, of course, much more bigger problems that we can solve in theory when we get more access to more and more qubits. Of course, you can see that 2,000 qubits like now, where the studies have been done, is quite limiting. But then, when you see all of this coupling taking place with 0 and 1s, and you steer all the couplers, you have lots of, let's say, influence on this. And then think about when this is collapsed, when basically the annealing process is finished, these kind of 0 and 1s give you the best or near optimal solution to your optimization problems in 20 milliseconds. So this is, of course, now the interesting effect on it. Again, the GitHub access to notebooks is there, is open. We just will open it when we have the acceptance of the paper, if we have the acceptance, but we are hoping to get it. Otherwise, of course, I'm also there tomorrow to talk about it. Hence, when I conclude here a little bit on the application problem, when we think now really comparing it one-to-one with the normal SVM, we can see that we have almost similar results, right? In terms of accuracy, things which matters, ROC curves and so on. It's getting more into detail, so I encourage you, of course, to read the paper that has much more details. In this sense, let us rather look a little bit on how to compare this now, right? So what is the demystifying effect here? And this is surely that it doesn't work for general purpose computing, quantum computing, and of course big data, as you have seen, 500 samples, in terms of high-performance computing, parallel I/O, and lots of big data. That's not much yet. And then also you have the programming scene, not so really extremely friendly. It's actually much more complex with lots of optimization problems that you have to develop to come that way. But there are 2 benefits why people actually consider quantum computing to be quite good. And this is the time to solution. As I mentioned, 20 milliseconds is quite something for an optimization which has a global minimum or almost the best solution. And then something I didn't talk as a concluding remark here for the quantum elements, the smart energy. The same problem takes on a HPC machine 2,500 kilowatts, but on the qubit machine or on an annealer, 25 only. And this is a scaling property. If we add more and more qubits, this is not increasing very much. While we add more and more high performance capacity, this is increasing heavily with chilling down and so on. So in this sense, you see it's also a future in terms of smart computing respective to energy. Right, and of course, I just scratched the surface here. Quantum computing is deep and is large. I encourage you to study it. If you want to know more, we are tomorrow in the Silverberg so I will be there any now and then. Please feel free to ask me more about the details of the quantum SVM, more of the quantum annealer, how you do your first baby step, which is actually happening and possible tomorrow. And of course, we teach also at the University of Iceland, HPC and cloud computing, where also quantum computing will play a role starting from next year. With this, just selected references for the uploaded talk, but more notably, the team that is behind all the efforts, so joint PhD students of Juelich Supercomputing Center and the University of Iceland since, let's say, 7 years. With this, thank you very much. Thank you. Thank you.
Thank you very much, Morris.